Hi, it's time for another math easy solution. Today I'm going to go over further into infinite series and sequences and now look at another segment of that section in my calculus book and go over the integral test and estimate of sums. So yeah, it's going to be another very long video. So like always, if you don't have time to watch the whole video, you can skip the end for summary and conclusions. This one doesn't have any, but if available. And also, you could also play this video at a faster speed and use the browser extension that I highly recommend. And yeah, it's a top secret life hack. Your brain gets used to faster speed. Very interesting. And also, you could download and read the notes as well as viewing the notes on Steemit. All the links will be in the description below. You could also watch a video in parts. Doesn't need to be all in one go unless you can do it. Then all the power to you. And also note number 2, if this video or any other video is volume's too low, you could always use this other extension that I recommend. Anyways, going further, so topics to cover. And the topics to go over are the introduction to the integral test and estimate of sums, then go over the integral test, going over example 1, example 2, which is on the P-series, and then theorem 1, which is also about the P-series, then go over example 3, example 4, and then go over estimating the sum of a series, and then look at theorem 2, which is a remainder estimate for the integral test. Look at another example, example 5, and then theorem 3, example 6, and then we're going to go over the proof of the integral test, which I'll go over the integral test initially, and then later I'll prove it at the end of the video. Anyways, let's go further. So, introduction to the integral test and estimate of sums. In general, it is difficult to find the sum of find the exact sum of a series. Remember, series is just a sum of a sequence. If we were able to accomplish this for geometric series, and the series, series right here is summation of 1 divided by n times n plus 1 in my earlier videos. Because in each of those cases we could find a simple formula for the nth partial sum, Sn. But usually it isn't easy to compute limit as n approaches infinity of S of n. Yeah, usually we can't compute the limit as the partial sum goes to infinity, or even find this partial sum. Therefore, in the next few sections, we develop several tests that enable us to determine whether a series is convergent or divergent without explicitly finding its sum. In some cases, however, our methods will enable us to find good estimates of the sum. Our first test involves improper integrals. We begin by investigating the series whose terms are the reciprocals, or i.e. multiplicative inverse. For example, 1 over 2 is a reciprocal of 2, since 1 over 2 times 2, so you multiplied, or the multiplicative inverse, you multiply by its inverse, equals 1. Like that, so 1 over 2. So for example, 1 over 3 would be the reciprocal of 3. So we're asked, we begin by investigating the series whose terms are the reciprocals of the squares of the positive integers. So yes, that's wording is a mouthful for my calculus book. But anyway, so what I mean by that is, let's take the summation from n equals to 1 up to infinity, and this is going to be, well, the reciprocal of the positive integers, but the square of them. So we're going to go 1 over n squared. Yeah, so that's the positive integer. So in other words, it's going to be summation of 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. So it's a reciprocal of the positive integers of the squares of the positive integers, hence the squared over there, plus 1 over 4 squared plus 1 over 5 squared plus ... and go on. Alright, so yeah, so there's no simple formula for the sum Sn, or the partial sum of the first n terms, but the computer-generated table of values below suggests that the partial sums are approaching number near 1.64 as n approaches infinity, and so it looks as if the series is convergent. And here's the table. And I must note the Excel file in the link below will be used throughout this document, so make sure to download and play around with it. So I have it in there. So here is the table, and here's all the way to 5,000 terms there. So we have term is 1 over n squared. So I just put this inside, divide it out. So 1 over 1 squared is just 1. And then 1 over 2 squared is going to be 1 over 4, so 0.25. And then this is the summation of them. So 1 plus 1.25, or I mean 1 plus 0.25 is equal to 1.25. And then 1.25 plus 0.1111 there, we get this over here, 1.36111. And so on, they go all the way to 5,000 terms, we get this 1.64 figure. So yes, it appears to be approaching, because remember, the first term is 1, and then it goes all the way here, the summation of all of them, you just get to 1.64. So it does look like it is converging, but that's not fully proof. But what we can do is we can confirm this impression with a geometric argument. So the figure below shows that the curve y equals 1 over x squared and rectangles that lie below the curve. And I'll actually draw that right now. So let's say we have like this. This is the x, that's the y. And let's say we have our function y equals 1 over x squared. So let's say it looks like this. This is going to be y equals 1 over x squared. So as x gets larger, this is going to be divided by a large number, so it's approaching 0 like that. Yeah, or actually, let's make this a bit more steep, just like this. Alright, and now what I'll do is I'll just write this 0 there. And let's say we have our first term, or our first x coordinate 1, then we have 2, then we have 3, then we have 4, then we have 5 here, and so on. And here I quickly just change the curve again just to make it a bit more presentable, because I'll be drawing some rectangles. So what we have here is, let's draw a rectangle from this 1 coordinate there all the way up top here, and it goes like that. So now this distance from here to there, that's just 1. So in other words, we're going to have a rectangle here with height. So this height right here is going to be, well, 1 is going to be the y, so 1 over 1 squared. In other words, this area equals 2, this is going to be 1 over 1 squared times 1. And yeah, that always going to be times 1 there, so this is going to be 1 over 1 squared. That just equals to 1 for this first one, like that. But likewise, I'm just going to erase this. It's pretty straightforward. So likewise, from this rectangle here, what we end up having is, then this goes like that. This area here, this is area equals to, well, 1 over, this new y is going to be 1 over 2 squared. And then times by 1, like that. So it's going to be 1 over 2 squared. And likewise over here, we'll have another rectangle like this. And this one's going to be area equals to 1 over 3 squared. And then we have another one here. Notice how it's always below the curve. So here, and this is our series that we were looking at. 1 over 3 squared. 4 squared, like that. And then finally here, we got just another fifth one. This area here is, I'll just put it here, area equals to 1 over 5 squared. So yes, here I've written up here. So the base of each rectangle is an interval of length 1, as I drew over there. The height is equal to the value of the function 1 over, y equals 1 over x squared. So here, like that. At the right endpoint of the intervals. For intervals from 0 to 1, we look at the right endpoint. From 1 to 2, we look at the right endpoint 2, and so on. So the sum of the area of the rectangles here, what these end up becoming are, if we just sum up all those rectangles, we have 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared, and it keeps going on and on. You can keep going on to infinity. So we get equals to, like this, equals to the summation from n equals to 1 up to infinity of 1 over n squared. Alright, now if we exclude the first rectangle, since f of x goes to infinity as x approaches 0, so here if we just exclude this one right here, just so we don't need to deal with this infinity function going all the way to infinity as x approaches 0, because 1 over 0 is infinity, so just so we don't need to deal with it. So the total area of the remaining rectangles is smaller than the area under the curve y equals 1 over x squared, for x is greater than or equal to 1. So here, if we look at these rectangles, sum those are all those up, those are going to be less than the area underneath this function, because you can see that there's a remainder every single area here. This gets smaller and smaller as this goes further and further. And yeah, so it's smaller than that, which is the value of the so that area of the underneath this curve, which is going to be greater than the rectangles area, which is the value of the integral from 1 to infinity of 1 over x squared dx. So again, 1 instead of the 0, so you don't need to deal with the second infinite. So recall in my earlier video on improper integrals that this improper integral is convergent and has a value of 1. So it's from a Steemit right here, the Steemit notes in my earlier video several years ago. This is improper integrals, type 1 and infinite intervals. So yes, when we have an infinity sign, it's going to be an improper one. We're going to have to, what I showed in that earlier video here, and I just took a screenshot of the calculus notes, because they're a bit neater than mine, and more compact. So here's the function y equals 1 over x squared. So if we take the integral or the area underneath this from 1 to t is going to be, well, 1 over x squared, take integral, you get this 1 minus 1 over t. That's the area underneath it up to t, and then we take the limit as t goes to infinity, and it's going to be 1 minus 1 over infinity goes to 0 there, so equals 1. So that entire area is going to be going towards 1, and hence it's convergent, and it has a value of 1. So the area of the shaded region approaches 1 as t approaches infinity. See figure there. So we say that the area of the infinite region S is equal to 1, and we write over here that the integral from 1 to infinity of 1 over x squared dx equals to the limit as t approaches infinity of 1 from 1 to t of the integral of 1 over x squared dx equals to 1. So the picture shows that all the partial sums are less than, and here's put in brackets, including the first rectangle. So that's going to be, well, the first rectangle is going to be 1 over 1 squared. And then we're going to take it's going to be less than this, remember this. Then it's going to be less than the area underneath the curve, which is 1. So the area underneath this curve here. So we're going to add this up right here, and then area underneath the curve. So the first area plus, and then it's going to be less than this right here. Integral from 1 to infinity of 1 over x squared dx. And this one right here is equal to 1. So this, or I'll just put this like this. This equals to 1. Then add these up, that's just going to be 1 plus 1 equals to 2. So the total area of those partial sums has to be less than 2. Yeah, so thus the partial sums are bounded. So yes, they don't go to infinity, they go to below a certain number. So we also know that the partial sums are increasing because all the terms are positive. So you're always, yeah, so you have this 1 over n squared right here. This number is always positive, so you're always adding to it. So it's always gradually increasing, because the terms are positive. Therefore, the partial sums converge, and this is by the monotonic sequence theorem from my earlier video on infinite sequences and series. So the series is convergent. Thus, the sum of the series and the sum of the series, or the limit of the partial sums, same thing, is also less than 2. So what we could do is write like this: infinity n equals to 1, and I'll recap on monotonic sequence theorem soon. So 1 over n squared, like this. This equals to 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared plus ... This is all less than 2. So we have concluded by using just integrals there. That's less than 2 there. Now recall the monotonic sequence theorem from my earlier video on infinite sequences, and here's a SteamEd article from there of the video notes, as well as here's the screenshots from the calculus book just for more compactness. So a sequence here, it's the monotonic sequences. Here's every bounded monotonic sequence is convergent, and this is the definition. Just to recap, sequence an is called increasing if an is always less than an plus 1 for n is greater than 1. That is a1 is less than a2, less than a3, and so on. It is called decreasing if it's the opposite, an is greater than an plus 1 for all n greater than 1. It is called monotonic if it is either increasing or decreasing. So yes, it's increasing or decreasing, it's monotonic. And so this one we have it's increasing, so it's monotonic there. And a sequence an is bounded above if there is a number m such that an is less than m for all an greater than 1. And since the function is going to be less than 2, it's going to be obviously bounded. Yeah, so you can't keep going higher and higher, and it's going to be bounded above, since an is less than m for all n is greater than 1. And likewise, it is bounded below if there's a number m such that the reverse an is greater than lowercase m for all n is greater than 1. If it is bounded above and below, if it is bounded above and below, then an is a bounded sequence. So yes, if it can't go below at a certain point or higher than a certain point. And the one we're dealing with, well, it can't go below. It can't go below 1 because it's always increasing, or it's always decreasing its value, but it's positive, so increasing the partial sum. So yes, it can't go below this one here because you're always adding more and more to it, and so on. So going further, and then so yeah, there's a monotonic sequence. Every bounded monotonic sequence is convergent. Essentially, just to recap on it more, if a sequence is always increasing or decreasing, hence monotonic, and is bounded above or below, then it will approach a number or limit L, which is less than capital M, or L is greater than M, or greater than or equal to M if the sequence is decreasing. For example, here, if it's going to be less than this this number m, there's going to be some sort of limit. It could be equal to m there if it's bounded below. And then, so yes, this just converges all the way to it. So there's a limit of that. And that's pretty much a monotonic sequence because this one's always increasing and it's bounded above, below, and so on. Note that the exact sum of this series was found by the Swiss mathematician Leonhard Euler, 1707, 1783, that's who he was born and died, to be pi squared over 6. But the proof of this fact is quite difficult, so I will have to prove it in a later video, and it's another problems plus video, so I'll do that much later on. Alright, so now let's take a look, or let's look at the following series, and it's going to be a slightly different one. So instead of doing the squares, we do the square roots. So we have 1 over, from sum from n equals to 1 to infinity of 1 over square root n. So this equals to 1 over square root 1 plus 1 over square root 2 plus 1 over square root 3 plus 1 over square root 4 plus 1 over square root 5 plus dot dot dot, and it just keeps going and going. Yeah, so the table of values of Sn, of the partial sums of these, suggests that the partial sums aren't approaching a finite number, so we suspect that the given series may be divergent, and that this table is again from that same Excel sheet. And here's the terms from 1 all the way to 5,000 there. And here's the term 1 over square root n, or n to the power of 1/2, same thing. So 1 over square root 1 is 1, and so on. Here's 0.707 for square root 2. And then here's his partial sums where we add these up. So when we add these up, 1 plus 0.7, we get 1.707. And then we go to 5,000. Notice this one's 139. So the thousandth term, thousands partial sum is 61. Before is 43 for 500. So yeah, it just keeps going bigger and bigger. Again, we use a picture for confirmation, because so this case looks like it's divergent. So the figure below, below, just added the text, shows the curve y equals 1 over square root 2, or x to the power of 1/2. But this time we use rectangles whose tops lie above the curve. So here I'll draw this one out. So what we end up having is like this. So there's the x, there's the y, and this curve is going to be, it's not going to be as steep as before. It's going to be more like this. Let's draw it a bit better. It's going to be something like this. All right. So let's say we have that. This is our y equals to 1 over square root x curve, like that. Let's draw our coordinates here, or the x-axis. So there's 0. Let's say we have 1 is going to be somewhere here. 1, then we have 2, then we have 3, and then we have 4. And here I just shifted everything, added the 5th one there, and then made the curve a bit more to the left so that we can do better drawings. Yeah, so we're going to draw the rectangles above the curve. So in other words, if we start from here, we're going to use the left endpoint as opposed to the right one. So the rectangles can go across this way, like that. So that this area right now, this height is going to be, well, 1 over square root 1 is the height. And then the width is just 1. They're all going to be separated by 1. So this area inside is equal to, well, 1 over the height times width. And yeah, that's just times 1. So 1 over square root 1 times 1, which is just going to be that. And then likewise for this side here, we're going to get, you can use the left endpoint so that the rectangle is always above the curve. So now we have the area here. This is using the left endpoint there too. This equals to 1 over square root 2. And likewise, we go across like that. And then we use this one here. This one is also area. Now we use the third one, equals 1 over square root 3. And then finally here we'll go like that. It's going to look something like this, where this area is equal to 1 over square root 4. Again, times 1, that's just unit length, so it just remains the same. Yes, and so on. This one's going to be the same thing across over there. And again, assuming this is always decreasing like that. Alright, so the base of each rectangle is an interval of 1, or the width there. The height is equal to the value of the function 1 over 1 divided by square root x, or x to the power of 1/2. at the left endpoint of the interval. So that's the value of this height there. So the sum of the areas of all the rectangles is, well, we just sum up all these rectangles like that. So it's going to be 1 over square root 1 plus 1 over square root 2 plus 1 over square root 3 plus 1 over square root 4 and so on. So 1 over square root 5 plus dot dot dot. This equals 2, right? This has a summation. N equals to 1 up to infinity, and this is going to be 1 over square root n. Yeah, so now this total area is greater than the area under the curve y equals 1 over square root x, for x is greater than 1, which is equal to the integral. So integral below this curve right here. So this is always above it, so it's going to be greater than the integral. I'll write it down like this. So yeah, it's going to be greater than this integral from 1 to infinity of 1 over square root x dx, like that. Yes, but we know from my earlier video that this improper integral is divergent, and this is from my earlier video, so yeah, if you hopefully you've been paying attention to my earlier videos from years back. So this improper integral is example 4, here's from Steemit as well, the video notes, and I've screenshotted the calculus version of the notes, just it's more compact. So for what values of p is the integral right here from 1 to infinity of 1 over xp dx is a convergent. So for what values of that is convergent, and then here the solution shows that, or from previous one, it showed that p equals 1 is going to be divergent, so 1 over x. And if p is not equal to 1, then there's the proof over here. So if over here it has if p is greater than 1, then the integral converges, but if p is less than 1, then over here the integral diverges, and it summarizes here as integral from 1 to infinity of 1 over x to the power of p dx is convergent if p is greater than 1 and divergent if p is less than or equal to 1. In other words, the area under the curve is infinite, because here we have this is 1/2, which is again less than 1, so that's the p, and that's less than 1. So in other words, the area under the curve is infinite, so the sum of the series must be infinite, because the area under the curve is infinite. So if this area under the curve is infinite, but these rectangles are more than that infinity, so that it's also infinity. So the series of so the sum of the series must be infinite, that is, the series is divergent. The same sort of geometric reasoning that we use for these two series can be used to prove the following test. The proof is given at the end of this section, and it's called the integral test. And this integral test states, suppose f is a continuous positive decreasing function on the interval from 1 up to infinity, and let an equals to f of n. And this f of n is the same thing as I've done over here. Notice here, this is, for this case, the an would be 1 over square root. Yeah, the area is just going to be 1 over square root 1. In other words, f of n here. So y equals f of x there, 1 over square root x. But that was just a specific one. I'll go over the general proof in later in this video at the end. So yes, if we're given this, then the series right here from summation of n equals 1 up to infinity of an is convergent if and only if the improper integral, and I'll write this down right here, 1 to infinity of f of x dx. Yeah, so if this is convergent, we'll just delete the empty space. Yeah, so this is, the series is convergent if and only if the improper integral right here is also convergent, or is convergent, then the other one would be. So in other words, if what we have is, if the limit of, or the integral from 1 to infinity of f of x dx is convergence, is the I part of it, then the series summation from n equals 1 to infinity of an is also convergent. And but then if this isn't convergent, so I'll just write this down again for completeness, if integral from 1 to infinity of f of x dx, so if this is divergent, so if that integral underneath, or the area underneath the function is divergent, then what we have is the series from n equals 1 to infinity of an is divergent. So yes, exactly as those two examples I did above. And note that when we use the integral test, it is not necessary to start the series over the integral at n equals 1. For instance, in testing the series, if we want to test this one right here from n equals 1 to infinity of the summation 1 over n minus 3 squared, actually instead of 1 we have 4. Yeah, so if we're starting from n equals 4 like that, we use, instead of n equals 1, we use n equals to, we use n equals to 4. So we go from the integral from 4 to infinity, not 8, infinity, like that, of 1 over x minus 3 squared dx. So yes, it doesn't necessarily need to be n equals 1. And also, it is not necessary that the function f be always decreasing. What is important is that f is ultimate, or be ultimate decreasing. That is, decreasing for x larger than some number n. So yes, as it goes to infinity, as long as there's some number that greater than it is always decreasing. Then the series, or the summation n equals capital N up to infinity of an is convergent. So this is also convergent if we start from n equals 1 to infinity of an is convergent by note 4 in my previous video on infinite series. So it doesn't need to always be decreasing as long as eventually it starts decreasing greater than a number. And this is from note 4 in my infinite series video, again from Steemit. There is a screenshot from my calculus book. So a finite number of terms doesn't affect the convergence or divergence of a series. For instance, suppose that we're able to show that the series right here, summation from n equals 4, as opposed to n equals 1, to infinity of n over n cubed plus 1 is convergent. So if that's convergent, since we have here, we have like this. So if you're looking at n equals 1 to infinity of n over n cubed plus 1, then we could just add the first three terms. So 1 over 2 plus 2 over 9 plus 3 over 28 plus this one's convergent. So because this one's convergent, this is just summation of just finite terms. So it follows that the entire series, from n equals 1 to infinity of n over n cubed plus 1 is convergent. Similarly, if it is known that the series right here from the summation from n equals capital N plus 1 to infinity of an converges, then the full series starting from n equals 1 an to of n equals 1 to infinity of the summation an equals 2 from n equals 1 up to capital N of an plus n equals capital N plus 1. To infinity of an. So yes, these are just finite terms. These are just finite. This one you're going to infinity. As long as that converges, then everything else converges, because these are just finite terms. So that's also convergent. So yes, that follows exactly as I was stating here. It does not need to be always decreasing as long as eventually it's decreasing. Alright, so now let's look at example 1 just to test out this integral test. So test the following series for convergence or divergence. And we have here from n equals 1 to infinity of the summation 1 over n squared plus 1. So now this is 1 over n squared plus 1. As you can see here, as you increase the value of n, this becomes what you're dividing by, or this terms become dividing by a larger number. In other words, it starts to decrease as you increase n, so it's decreasing. And it's also, here it's always positive. So it's always positive and it's always decreasing, and it is continuous because there's no discontinuities here. You can't make the bottom 0. So the function f of x equals 1 over x squared plus 1, so just replace it with x to get the function. It's continuous, it's always positive, and it's decreasing from interval from 1 to infinity. So we use the integral test, and the integral test is, again, just take the integral 1 over, integral from 1 to infinity of 1 over x squared plus 1 dx. This equals 2. This equals 2. So we can take the limit as t approaches infinity of integral from 1 to t of, again using improper integrals techniques, 1 over x squared plus 1 dx, like that. And now to solve this integral, I have to recall from my earlier video on the derivative of inverse tan of x, or tan negative 1 of x, or arctan or arctangent or whatnot, however you want to call it. From my earlier video, there's a link to it, one of my very earlier ones. And then if you go through that proof, it goes over it and it shows that d over dx of inverse tan of x is equal to 1 over x squared plus 1. So in other words, we can take the antiderivative or the integral and to get back to this one right here. So that's what we can simplify that. So thus we have, thus this part right here, limit as t approaches infinity of from 1 to t of 1 over x squared plus 1 dx. This equals to, this equals to the limit as t approaches infinity, and then we could just box this inside, and that's going to be our, this is going to be the antiderivative, is going to be tan, inverse tan of x, like that. So you take the derivative, it gets over that, like that, and this is going to be from 1 to t. So this equals to, we're going to have a equals to a limit as t approaches infinity of now we're going to have a brackets tan inverse tan of t, inverse tan of t minus, put a bracket like that, minus tan of 1, like that. And now to solve these two parts right here, and this one as t approaches infinity of that one, what I want to first calculate is, or solve, is this one first right there. So let's put a line here, recall or note, basically using exact trig ratios, but here we can just go easily and draw a square. So we draw a square with sides 1, 1, 1, like that. And I'm going to split this in half. So the angle here is going to be 90 degrees or perpendicular, or in radians pi over 2. So what I'm going to do right now is draw this, or cut this in half, so that the angle's divided by 2. So in other words, now we have, this is going to be 45 degrees, or pi over 2 divided by 2, it's going to be pi over 4. And this is going to be pi over 4, like that as well. So now, this is a right angle. So what we can do is just take the tangent, recall tangent of this angle, pi over 4, is defined as opposite over opposite over adjacent. Adjacent. So if it's like that, this just, the opposite is just 1 divided by 1, is the adjacent. So we have 1 over 1, that equals to 1, like that. So that's 1 over 1 equals 1. So now, but we want to know the inverse tan. Remember, inverse, all we do is switch the x and y, or switch this with that one. So in other words, we get the inverse tan of 1 is just equal to pi over 4. So tan pi over 4 equals 1, the inverse is going to be, you switch those around. So the inverse of, inverse tan of 1 equals to pi over 4. So there is that this value. This is just pi over 4, like that. And now this one here, we have to take a limit there, so that's going to be a bit interesting there. So I'm going to draw this again. Yes, and here I'm going to write also recall. This one, also recall trigonometry. Very interesting stuff. So we'll have a curve like this, y, and there's the x, there's the y, and then what I'm going to do is I'm going to recall the graph of tangent. It looks like this. It goes downwards like that, and for the inverse, it's usually defined from pi over 2 to negative pi over 2. So here, this curve right here is our y equals to tan. I'll start with tan of x. I'll put it over here. So this is y equals to tan of x, like that. So we have that, and this line right here, asymptote line all the way going down, like that, and this asymptote line is at pi over 2, and then this asymptote line across here is at negative pi over 2, like that. And here, actually, just to align with this t there, I'm going to write this as t, change the variable from x to t. Yeah, so now to draw the inverse, I'm just going to write inverse, or better yet, write it in red. So inverse is effectively just switching the y and x, or the coordinates around. So switching x and y to y and x. So in other words, here, so if this one's here, if it's approaching, y and t in this case, actually, t and y, and y and t. So if as t approaches pi over 2 here, this goes to infinity, so then the reverse is going to happen. So that as t approaches infinity, then the y goes to pi over 2. So we could draw the asymptote lines like this. It's going to be across like that. and then likewise for here. So as t approaches negative pi over 2, then y goes to infinity, but instead it's going to be opposite. So then as y approaches negative pi over 2, t goes to infinity, or negative infinity, because this is going negative infinity like that. So we'll just draw asymptote like this. This is like that, and this is going to be, and I'll write this down, this height is pi over 2. This one's going to be negative pi over 2. So then this is going to be inverse in every way. So it's going to go, yeah, it's going to start here, it's going to just touch it and then go all the way across like that. And likewise here, it doesn't actually overlap, but instead it goes like this. Let's draw this a bit better. Oops, draw this a bit better. Yeah, like that, and it goes all the way. Yeah, so draw it better like that. And this is the inverse. So y equals to tan inverse of t, like that. Yeah, so here as t is going to infinity, over here, as you can see, let's write this there. T is approaching infinity, then y is approaching pi over 2. So the inverse of this one there. So we could, yeah, this is going to be reaching pi over 2. Yeah, so we'll just put it down here. So this one right here is, yeah, this is approaching pi over 2 as you plug in that t goes to infinity there. This one has no t, this one has no t there, so it's just pi over 4. So what we end up having is, so thus we have, yeah, so that's the integral. So the integral right here of 1 over infinity, just from the beginning. So 1 over, no, so integral from 1 to infinity of 1 over x squared plus 1. So right here, write it all down here. So integral from 1 to infinity of 1 over x squared plus 1 dx. This equals to pi over 2. Yes, yeah, finally, so pi over 2 minus pi over 4. But pi over 2 just times it by top and bottom by 2 over 2. This just equals to, well, 2 pi over 4 minus pi. That's just 2 pi minus pi. This equals to pi over 4. Like that. And there we have it. Yeah, pi over 4. Fascinating stuff. Yeah, so thus what we have is the integral from 1 to infinity of 1 over x squared plus 1 dx is a convergent integral. And so by the integral test, the series, as well as, yeah, because the integral is convergent, thus the series is as well. The series of 1 over n squared plus 1 is also convergent. So yes, fascinating stuff. Alright, so now let's go over example 2, and this is on the p series, and it states, for what values of p is the following series convergent? And we're given the summation n equals 1 to infinity of 1 over n to the power of p, hence p series. So let's check some easy values for p. So if we have p is less than 0, then what we end up having is 1 to the 1 divided by n to the power of to a negative power, which gets flipped, it becomes positive. So then what we have is limit, so that each term limit as n approaches infinity of 1 over n to the p. This is going to be equal to infinity. This is going to approach infinity because, i.e., let's put an arrow. For example, if we had n to the power of if we had something like 1 to the power of, 1 divided by n to the power of negative 10, this gets flipped upside down, so this becomes n to the power of 10. So the negative power, recall, you just flip it up. You can see this in my earlier videos on power functions. Yeah, so this is positive, and then as you're going to infinity, you're going to have infinity to the power of 10, or even if it's 0.1, doesn't matter what it is, it's going to be a positive power, it's going to go approach infinity because it's always positive and increasing. So hence, if p is less than 0, that is divergent. And it's, yeah, so the terms are going to infinity themselves. And now if p is equal to 0, let's see what we have here. So if p equals 0, then what we end up having is a limit as n approaches infinity of, well, 1 over n to the 0. And recall this is defined, yeah, my earlier video is defined it as equals to 1. So this just equals to, yeah, so this right here, put an arrow, equals to 1. So in other words, this whole thing is equals to 1. Limit of 1 over 1 as n approaches infinity is just 1. The n is gone, like that. So then all the terms are 1, so you're going to be summing here, 1, 1, 1, 1, 1, so those are going to be divergent as well. So yes, in either case, the limit as n approaches infinity of 1 over n to the power of p is not equal to 0 when p is equal to 0 or p is less than 0. So the given series diverges by the test for divergence, also from my earlier video on infinite series, and it's from the same one here. Here's a screen cap from the calculus book and the link to the Steemit notes again. So if the series right here, n equals 1 to infinity, the summation of an is convergent, then the limit as n approaches infinity of an has to equal to 0. So if it's convergent, this has to be going to 0 as well. And there is the proof for reference. Again, you could see the earlier video to see it in more detail. And yeah, just to note, the opposite of this theorem is not true in general. So if the limit n approaches infinity of an is going to 0, we can't conclude that the whole series is convergent, because that harmonic series, as I showed before, it diverges even though that the terms are going to 0. And likewise, the test for divergence, if the limit an does not exist, limit an as n approaches infinity does not exist, or if limit n approaches infinity, an is not equal to 0, then the series an as n approaches n equals 1 to infinity is divergent. So yeah, so this is exactly what we have here. This one here it doesn't exist, it goes to infinity, and this one equals to 1. So thus, by test of divergence, that series is divergent. So the test of divergence follows from Theorem 6. Because if the series is not divergent, then it is convergent, and so limit as n approaches infinity, an equals 0. So yes, for our case, if p is greater than 0, then the function f of x equals 1 over x. P is clearly continuous, and it's also positive. Yeah, it's continuous because you can't divide it by 0 there. You can't get a 0 at the denominator, so it's always continuous. It's always positive because every number is just positive there, and it's decreasing because as you increase the value of x right here, you're going to be dividing by a bigger and bigger number because this is positive, p is positive. And yeah, so it's always going to be, the bottom always gets bigger, so that's the 1 divided by increasing means it's decreasing. So it's decreasing on the interval from 1 to infinity. And recall from my earlier video on improper integrals, which I mentioned above that, yeah, the one I went over earlier, so this one here. And let's just scroll up to that exact spot where I referenced that over here. Actually, scroll up more, so all the way over here, and it's a summary of the example 4 there. So this integral from 1 to infinity of 1 over x to the power of p dx is convergent if p is greater than 1, and divergent if p is less than or equal to 1. So for values p is greater than 1, well, we know that's from my earlier video that it is convergent. So it follows from the integral test, the series summation of 1 divided by n to the power of p converges if p is greater than 1, and diverges if it's between 0 and 0 and 1 there. So if it's greater than 1, it's going to be divergent, and if it's less than that, and in our case, if it equals 0 as well, or if it's less than 0, it's also diverges. So going further, and note that I briefly mentioned as well, note that for p is equal to 1, this series is the harmonic series, and which I discussed in my previous infinite series video as well. So yes, make sure to watch my earlier videos because it's everything follows up in all other videos. So recall this one here. So if p is equal to 1, we have 1 over n to the power of 1. So that's just harmonic series. We get 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. And then the proof that I showed, it was actually divergent. So yes, so this is actually divergent there, even though that the actual 1 over n, the limit of that term goes to 0 as n goes to infinity. So note that in order to use integral tests, we need to be able to evaluate the integral from 1 to infinity of f of x dx, and therefore we have to be able to find an antiderivative of f. So yes, we need the antiderivative. Frequently, this is difficult or impossible. Again, like that other one where I showed that you have to get the inverse tan, and that was a somewhat difficult one too, because you have to find out an antiderivative that isn't used that often, well, at least for me. But sometimes it's difficult or impossible to even find any antiderivative. So we need other tests for convergence too. The series in example 2 is called the p-series, and it is important in the rest of this and later videos. So we summarize the results of example 2 for future reference as follows. So theorem 1, p-series. The p-series right here, 1 over n to the power of p, for n is equal to 1, summation up to infinity, is convergent if p is greater than 1, and divergent if p is less than or equal to 1. So just keep that always in mind. And now let's look at example 3. So the series over here, summation from n equals 1 to infinity of 1 over n cubed, is going to be 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed plus etc. Keeps going on. And this is going to be, well, the p test, p is greater than 1, p is 3. So it's convergent because it is a p series with p is equal to 3, which is greater than 1. So yes, let's just use that test and we can quickly solve that. But over here, the series, summation from n equals 1 to infinity of 1 over n to the power of 1 over 3. So this 1 over 3 is going to be less than 1. So that's going to be obviously divergent. And you can also write it like this. Cubed root, so a summation of n equals 1 to infinity of 1 over cubed, 1 over n cubed root is equal to 1 plus 1 over 2 cubed root, and then the plus 1 over 3 cubed root, and then plus 1 over 4 cubed root, plus etc. And this is divergent because it is a p series with p equals 1 over 3, and that's less than 1. So yes, you could just use that theorem and quickly see if it diverges or converges. And I want to make a note that we should not infer from the integral test that the sum of the series is equal to the value of the integral. In fact, as recall that I stated earlier, and I will prove in a much later video, the summation from n equals to 1 up to infinity of 1 over n squared, this is equal to pi squared over 6, whereas the integral is going to be, well, way off. It's going to be the integral from 1 to infinity of 1 over x squared dx. This is actually just equal to 1. So they are not the same in this case. And therefore, in general, we can't say they're equal. So in general, we'll say that they're not equal. So from the summation from n equals 1 to infinity of an, this series, is not equal to, in general, from the integral from 1 to infinity of f of x dx, like that. Alright, now let's look at another example, and this is example 4, and this states, determine whether the following series converges or diverges. And then we have over here the summation from n equals 1 to infinity of ln n over n, so a lot of n's over there. So remember, ln is just log base e. So solution to this, so the function f of x equals ln x over x is positive and continuous for x is greater than 1. So you just recall the graph of ln. It's always going to be positive after x is greater than 1. And I'll be illustrating that soon. And again, yes, it's positive and continuous because a logarithmic function is continuous as well. But it is not obvious whether or not f is decreasing, so we compute its derivative. So yes, from earlier videos, logarithmic function, yes, it is continuous. You can see those in the earlier videos. But again, this function not necessarily is increasing, because it's divided by x term there. So what we could do here, if we're looking at this the function version of the series, fx equals ln x over x, first I'm going to do is recall the derivative of the ln function. So recall that d over dx of ln x is equal to 1 over x. And you can see this in my earlier videos as well. Yeah, so thus, the derivative of this function up top, so thus, let's just write it down, fx equals to ln x over x. So now, taking the derivative, so f prime of x equals 2, then we're going to take the derivative of ln x, and I'll just write this in more detail like this, d over dx of ln x. Then I'll put a bracket, and then I'm going to multiply by this 1 over x, and then plus the opposite of this, just to apply chain rule instead of using the quotient rule, because it's not as straightforward to memorize. So I'm just going to write ln x like this, times it by d over dx of 1 over x. So what I'm doing right here is just the chain rule. Should maybe put it like this. Chain rule, top there, where you basically take the derivative times the other function, plus then that function times the derivative of the other function. So this is going to be equal to 1 over x times 1 over x, like that, plus ln x And now the derivative of this 1 over x, that's going to be, well, let's just do this in more detail. It's easier to take the derivative as flipping this above so you don't have a denominator. So d over dx of x to the power of -1. So then let's just keep going. This is 1 over x times 1 over x. This is 1 over x squared plus ln x. Now the derivative of x power of -1, you bring it down to -1. Recall from the power derivative rules or derivative of power functions. So you bring down the -1 and then you minus a power. So it's going to be -1 like that. And then times it by x minus a power x -2, which is just 1 over 1 divided by x squared. So that's a negative. So this becomes, put this all together, this becomes 1 minus ln x, because you use the same common denominators, we'd make it minus, it's just x squared like that. Yeah, so this is our derivative. F prime of x is this, like that. And now to see if this is increasing or decreasing, I'm just going to recall on, just a refresher on inverse functions and this ln of x, or log base e. So recall, so if we have a function like this, y equals e to the x, then the inverse is such, such that if we were just to do, just switch the variables, is such that, we're just move it down here. It's such that if you switch the variables, so we're gonna have an x equals to e to the y. Then we need to just solve for the y. So if we solve for the y, we get the inverse of this function. So what we get is, and the solving for the y, this is defined as, defined as the inverse. So defined is going to be now to solve that y equals to log base e of x, for it's the inverse of that function there, like that. And now this equals 2, and then this is just conveniently written as ln, like that, ln of x. So log base e is ln of x, like that. Yeah, so this is what we have. So essentially, if we were to graph it out, y, what we'll end up having is, number e to the y, this x increases more than the y. So it's going to look like recall how the function looks like. And it's always going to be positive. I mean, the x is always going to be positive, but this one could be negative initially. And that is actually when x is less than 1. So I'll just draw this out. So if we have x, y like this, recall that the curve looks like this. So we're going to have something that looks like, extend this out, and it's going to go like that. That's how the log function moves. So it moves xy's more than it does upwards in the y direction because of this e to the y. So e to the y is makes x increase faster. So at this point right here, this is at x equals 1. So this is at 1. And recall that, remember, it's the inverse of this function. So if x is equal to 1, then this is going to be e to the 0. Recall that this is just e to the 0 equals to 1. And again, this by definition, e to the 0 is equal to 1. Any power to the power of 0, as I showed in my earlier videos on that. And now the interesting part here is, at this point right here, if this is e, that is e. So if x is equal to e, what we end up having as a value here, this is going to be, it's the same thing here. e to the what number here, I'll just put a blank. E to the question mark equals to e, that's just going to be, 1. So e to the 1 is equal to e. So yes, remember, it's just switch. So we're trying to find y. So if this is e equals e to the power of y, which is 1. So in other words, this value is all the way here. It's going to be 1, like that. I'll just draw some arrows like this, and so on, all the way across there. And this function is our y equals to ln of x, or log base e of x. So notice what we have here. So ln of x, so we have the x squared is positive. We have 1 minus ln of x. So if we want to know, we want to know if it's decreasing. So remember, we want to check if it's decreasing so that we could see if it's converges or diverges, or we could, or the other way around if it's increasing. So what we could do is, we'll just look at this graph. It's going to be 1 minus this ln of x. But then as ln of x here is greater than, it's greater than 1 over here. So it's only greater than 1 when x is greater than e. So here, put an arrow like this. This right here, I'll put just put a bracket here. So this is greater than, greater than 1 here. Or I'll just write y is greater than 1 when x is greater than e, like that. So that's in this upper region over there. Keep drawing more and more lines like that. Yeah, so thus, let's just write this down. So that's the derivative. Let's put this here. Thus, f of x, derivative of f prime of x is equal to 1 minus ln of x over x squared. This is going to be less than 0 or decreasing. Yeah, decreasing when we have when we have that, but let's put it over here. So when 1 minus ln of x is going to be less than 0, because this is always positive, and in other words, we just move this around, move the ln of x over there. We get a ln of x, make it positive and be greater than. I'll just make it less confusing to keep the same sign. Just move this over, so ln of x like that, and it's going to be greater than 1. Again, take the power of e on both sides, like that. These cancel, just different properties of the log function. So this cancel, we're going to have now x is greater than e to the power of 1, which is e. Exactly, I just showed here. So y is greater than 1 when x is greater than e. So in other words, greater than 1 minus a number greater than 1, it's going to be negative. So yes, so over there. Yes, so it follows that f is decreasing when x is greater than e, and so we can apply the integral test. And what we could do is take the derivative, I'm going to take the integral from 1 to infinity of ln x over x dx, like that. Now this equals to the limit as t approaches infinity, because improper integral of the integral from 1 to t of ln x over x dx, like that. Yes, and now recall to, or a note to solve this integral. Let's go put a note right here. Note that note that the derivative, so if we take the derivative like this of d over dx of this, the interesting part, because we have an x over there and there's a ln x, remember the derivative of ln x is 1 over x. So note that if we take the square of it, like that, so the derivative of the square, what we end up having is something that looks like this. We're going to have a 2 times ln x, and then by chain rule the inside, it's going to be, well, over x, like that. So we're going to have 2 times ln x times x. So in other words, we have this part right here is just that. Yeah, so that's the derivative of it. So then the antiderivative is going to be the opposite. So thus, the antiderivative is move this around over to the other side. Yeah, move this 2 over to the other side. So the antiderivative of ln x over x, like that, is going to be equal to the derivative, the antiderivative. So ln x, and move the 2 below it, divided by 2, and this is squared, like that. And for completeness, it's just an indefinite integral. This is going to be plus c, a constant c. So we can ignore that for the definite integrals. So what we could do now, so that's a note, and I'm going to do is put this in a bubble, just like that. And I'm going to put an arrow here, so let's write this down here. So we're going to get a limit as t approaches infinity of, now we're going to have that solving it in there. It's going to be over there, ln x over ln x squared over 2. So ln of ln x, like that, squared over 2, and then from 1 to t. And now let's just put this all the way down here and solve it. Thus, what we have, let's put an equal sign, so equals, just to extend this calculation. So we're going to have now limit as t approaches infinity, and then just plug this inside. So ln t over 2 squared, like that, bracket minus, and then this is 1, like that, so ln of 1, ln 1 squared over 2, like that. So this one is ln 1. Let's just look at our chart right here. So ln of 1, so when x is 1, we have e to the 0, equals 1, actually I get that wrong. So this is the 0, so that's the y. So at x equals 1, we have y equals 0. That's just, again, that's e to the 0 equals 1, since it's all reversal, so the y is there. So if x is 1, y is 0, like that. So this is going to go ln 1 is 0. 0 like that. So this equals 2 limit as t approaches infinity of ln t squared over 2. And ln t, well, that just goes to infinity. This just keeps going up and larger and larger. That's just our y function. So this just goes to infinity. Like that. Yeah, so since this improper integral is divergent, the series itself is divergent again by the integral test. You just got to check if it's decreasing, positive, and continuous. Then you got to check if the integral diverges. If it does, then the series itself, the summation of ln n over n from n equals 1 to infinity, is also divergent by the integral test. And if it's otherwise, if it's convergent, then it will be convergent as well. So this improper integral, if it was the reverse, it would have been convergent as well here. So now estimating the sum of a series. So suppose we have been able to use the integral test to show that a series an is convergent, and now we want to find an approximation to the sum of the series. So yes, now we want to know more than just if it's convergent or not, and then see if we can approximate the actual value. So of course, any partial sum Sn is an approximation to S, because the limit as n approaches infinity of the partial sum S of n equals S. But how good is such an approximation? To find out, we need to estimate the size of the remainder. Yes, then we can write this down in formula form as Rn, the remainder after the nth term is equal to S minus S of n. So that's the actual sum minus the partial sum Sn all the way there. And this just equals 2. Well, it's going to be the terms an plus 1. So after the nth term, an plus 1, an plus 2, plus, and then an plus 3, and so on, like that. So we're all adding all the rectangles as I'll show past, or all the terms past the nth term. Yes, so the remainder Rn is the error made when Sn, or the partial sum Sn, the sum of the first n terms, is used as an approximation to the total sum. And we use the same notation and ideas as in the integral test, assuming that f is decreasing on the interval from n to infinity, and comparing the areas of the rectangles with the area under y equals f of x for x is greater than n. In the figure below, we see that, and I'll draw this one out. Yeah, we see like this. So if we have the x and y, so there is the y axis, and there's the x like that. This is the y. So let's say we have a function like this, draw it like this. This is the y equals f of x. And let's say this is all the way, let's see, there's 0 there, but let's say we have all the way to our nth term, and it's all the way across here. This is our nth term. So we've summed up all before to the nth term, and now what we want to do is get the rectangles or the terms after the nth term. In other words, get the remainder. So what we'll do is I'll draw a point like here. This is going to be n plus 1, and this is going to be n plus 2, and so on. Then we have, and so on and so on. So I'll just draw like this. This part's going to go all the way across like this. I'm going to draw a rectangle from it. So now we have a, this is the term an plus 1. And now likewise over here, make it a bit closer like that. So we have this, and this is going to be our an plus 2, and so on. We're going to keep getting more and more like that. And these are all the terms after, all the terms after the nth term. And put a dot like that. Yeah, so that's what we have over here is Rn. Let's write this down. The remainder Rn is equal to an plus 1 plus an plus 2 plus ... And this is going to be less than or equal to, so it's going to be less than or equal to the area underneath, or the integral from n to infinity of f of x dx. Like that. Because in this case here, so n plus 1, we have the rectangle on the left, so it's going to be less than or equal to it. And here, just move the things around, just boxed it up like that. So yes, that's for this case. But now let's look at the rectangles on the other side. So similarly, we see from the following figure that, now we're going to use rectangles on the other side of it. So let's just draw the x and y coordinates again. So it's going to be like this. This is the x, there's the y, and we're going to have a function like this. Let's draw this like that. Okay, so we have a function. This is our y of x. Y equals f of x like that. And let's say we have our n is over here. There's our 0. So this is all the way up to the nth term. I'm just going to draw this one in black. And then we're going to go to the side like that. Like that, and so go all the way down here, and I'll write this as a n. So that's the nth term of the series, or of the sequence. And now in red, now we'll look at the remainder. That's going to be over here n plus 1. So we're going to go all the way across like that, and this one's going to be our a n plus 1, and then likewise we're going to have an n plus 2 there, and it goes like that, and this is our a n plus 2. And this is always going to be, yes, keeps going on and on, like that. And then let's do one more. Dot, 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 keeps going on. Notice this one is greater than the f of x curve there. Thus, what we have is the Rn, the remainder, is past the nth term, is going to be equal to a n plus 1. And then going further, a n plus 2. And then plus dot, dot, dot. But now instead of less than, it's going to be greater than or equal to the integral, or the area underneath this curve from, this is going to be from, this is going to be from n plus 1. So we're starting from this side there. So n plus 1 up to infinity of f of x dx, like that. Yes, and here I've boxed that out. So now that we have a remainder like that, yeah, remainder is greater than this n plus 1 from integral from n plus 1 to infinity of fx dx, and but likewise is less than from this part from n to infinity of fx dx. So we have proved the following error estimate. Theorem 2, remainder estimate for the integral test. So suppose f of k equals ak. Yeah, just defining that the function and ak they share the same function there, the series and this function f of x or f of k, where f is a continuous positive decreasing function for x is greater than or equal to n, and the series summation of an is convergent. So if it's convergent and it's continued, the function f is continuous positive decreasing for the function, and if we have the remainder Rn equals to s, the actual sum, minus partial sum s of n, then, so if that's what we have, then what we end up having is the integral from n plus 1 up to infinity of f of x, like this, dx. This right here is going to be, well, it's less than our Rn. So Rn is going to be greater than this, so the remainder is going to be greater than on this side, greater than the area under the curve when we're dealing with like this to the right of it, or above that function. So this is going to be less than or equal to Rn, like that. But then this is going to be less than or equal to over here. This one is going to be the integral from n to infinity of fx dx, like that. So the rectangles are smaller than that as well. And these rectangles are exactly the same. They're just shifted based on, well, they're just they're just shifted based on the curve there. So instead of this one, this can be shifted to the right, and so on. So this one's going to be like that. So it's going to be, so the error estimate, so the remainder is going to be less than this. Greater than this, but less than this right here. Yeah, less than this area of that curve. So going to be the integral from n to infinity of f of x dx, like that. And I'll box this out like this. It's actually pretty fascinating if you take time to think about it. Alright, so now let's look at another example, and this is example 5, and it states approximate the sum of the series of this right here, summation 1 over n cubed, by using the sum of the first 10 terms. So we just add those up. And then it states estimate the error involved in this approximation. And then part B says how many terms are required to ensure that the sum is accurate to within 0.0005, so 3 5s. Solution, before I get to a and b, in both parts a and b, we need to know the integral from n to infinity of f(x) dx. And with f of x equals 1 over x cubed, which satisfies the conditions of the integral test we have. So yes, this is satisfied. This is just a p series. This is always decreasing, and it's positive, and it's continuous, because we have 1 over x cubed right there. It's always going to be positive for x is positive. And it's decreasing. 1 divided by x cubed is always going to be decreasing. You're always cubing. The number is going to get larger and larger at the bottom. Dividing by large number is a small number. So what we have is we need to take the integral of it. So we need to take n to infinity to get the upper limit here. So we're going to go from n to infinity to get the upper limit to see how accurate it is. And let's just keep going further here. So of f of x dx, this equals to integral from n to infinity of 1 over x cubed dx. And this is an improper integral, so we need to do the same thing as always. Limit as t approaches infinity, and then I'm going to write this as n to t, and instead of writing 1 over x cubed, I'm just going to write this as x to the power of negative 3, just so it's easier to solve for the integral like this. The same thing. Power function, just put a negative, you can flip it to the bottom or the top. So we have this here, so the integral, recall the integral is an antiderivative. So in other words, to get this right here, before it used to be a x to the power of negative 2, or a higher power by 1. So this is going to be equal to, let's put the limit as t approaches infinity, put this in bracket, we're going to have x minus 2. And to get rid of that, because remember the chain rule, or when you take the, or not necessarily the chain rule, just the power rule, when you take the derivative, you have to put the negative 2 down. So what I'm going to do is I'm going to divide this by negative 2, because we're taking the antiderivative, like that. So that if you take the derivative of this one, you can put the negative 2 down, then minus a power, so then these negative 2's cancel, and over negative 3, like that. This is from n to t. Yeah, so what we end up having is, and then this is going to be limit as t approaches infinity, and now what I'm going to do is I'm just going to move this at the bottom again. So we'll move this as, this is going to be as 1 over negative 2, put the t inside, t squared, just to get rid of that negative power. And then we're going to have to minus, and then the n inside, so that's going to be 1 over, and then it's going to be negative, make this a positive like that, because it's the negatives cancel. So 2 n squared like that. So that's what we end up having. So what we end up having here as t goes to infinity at this one right here, well, we're going to have a scenario that's 1 over infinity, because t squared, infinity squared is just infinity. Yeah, it's also going to infinity, so then it's going to be 1 divided by infinity, it's going to 0. So what we end up having is, we have a term here, 0 plus this one here, there's no t term, so that's all we have. So 1 over 2n squared. So that is the that is the sum, or the integral from n to infinity. And this is the upper limit of that remainder. So the remainder is going to be less than, from integral from n to infinity of f(x) dx. So it's going to be less than this number here. So the whatever partial sum that you have, it's going to be less than this error, or this remainder part. So 1 over 2n squared. Or I mean, the remainder is going to be less than this. So it's going to be the larger and larger, or more and more terms you get, that n gets larger. So then you're going to have smaller and smaller remainder there. It's very interesting stuff. So yes, that's a good way to check the calculation as well, because this should get smaller and smaller as you increase the number of terms, because the increased number of terms you get more accurate. A more accurate sum, so then you're going to have to have a smaller and smaller remainder. So now let's look at part A. So now that we have that, so A, approximate this sum by using the first 10 terms, so summation 1 over n cubed. So what we'll write here is A. What I'm going to write is the summation from n equals to 1 to infinity of 1 over n cubed. This is approximately equal to this first 10 terms. I assume it's approximately, so my calculus book has this like that. That's approximately equal to the s10th, or the 10th partial sum, and this equals to 1 over 1 cubed plus 2 over cubed plus 1 over 3 cubed plus ... all the way until we get 1 plus 10 cubed And this, if you plug this into a calculator, you get it's approximately equal to, and this is going to be 1.1975. And here's just a calculation check. My OneNote has a built-in calculator, which is pretty amazing. So you just put this here, S10, 1 over 1 cubed plus 1 over 2 cubed all the way to over here, 1 plus 1 over 10 cubed. So here's the calculation. I'll delete this and write equal and then space, and yes, automatically calculates. Absolutely fascinating stuff here. Unbold that. All right, so yes, that is the correct one there. So according to the remainder estimate in Theorem 2, so the Theorem 2 is over here's Theorem 2 remainder estimate. So according to this one here, this remainder is going to be less than or equal to, this figure there, the integral from n to infinity of fx dx, which is this number right here, so we got to put a 10 inside there. Yeah, so what you end up having is r, instead of n, we have r10. It's going to be less than or equal to, and it's going to be integral from 10 to infinity of 1 over x cubed dx. And this right here, that's the 10, so we already know that. That's just going to be this one here. This is from n to infinity of fx dx, so it's going to be 1 over 2n squared, so 1 over 2 times 10 squared, or cubed like that. Actually, no, yeah, it is squared there, so that's this right here. 1 over 2n squared, like that. And this equals to, this just equals to 10 squared is 100, so what we end up having is 100 times 2, that's 1 over 200, like that. So the error is going to be less than, or the remainder is going to be less than 1 over 200. Yeah, so the size of the error is at most 1 over 200, which equals to 0.005, and you can just do that as well. Automatic calculations. Amazing stuff here. So yes, that's the error is at most that, which is pretty good for the first 10 terms. So 1.1975, so this is going to be a 5 in there somewhere. At most error. So that was the estimate error involved in the approximation. And now part B says how many terms are required to ensure that the sum is accurate to within 0.0005. So like a third zero there. So we want to see how many terms. So 10 terms you can be within 0.005, and now accuracy to within 0.0005 means that we have to find a value of n such that Rn is less than 0.0005. So what we'll do is write, well, since we know that Rn is less than or equal to, so yeah, we'll scroll up again. So Rn is less than or equal to the integral from n to infinity of fx dx, which that equals to 1 over n squared. So it's less than equal to n to infinity of 1 over n, 1 over fx dx, like that. And then this equals to, we already solved it for our case, 1 over 2n squared. Yes, in other words, what we want to be accuracy within that. So what we want is this, it has to be less than 0.005. So we want, the max error there, 1 over 2n squared less than 0.0005, like that. Yeah, so solving this inequality we get is, well, we can move the 2 over to the other side first of all. So what we get is a 1 over n squared is less than, 2 times 0.0005. And when we multiply that out, we just get a, this is 5 times 2 is 10. So we're just going to move it over here. We're going to have 2 zeros there. So this equals to 0.001. And now this equals to, just get rid of the decimal place to make it a fraction, because we have a fraction here. So what we'll do is move this over 1, 2, 3 decimal places. In other words, we're going to have this is the same thing as writing 1 over 3 zeros here. The 1 over 1,000. So 1 with 3 zeros, like that. So now what we have here is we can move this over to this side, and we can move over this to the other side to get rid of the fractions. So what we end up having is a 1,000 is less than n squared. Or in other words, take the square root. So we're going to have a n is greater than, move the the inequality across like this. So we have n is greater than, and then square root. Number square root could be plus or minus, but for practical use in this case, it's a positive. So 1,000 like that. And then this one right here, if you were to put this in a calculator, you're going to get a 31.6, so roughly that figure there. But n is greater than it. Yes, we need to be n is greater than it, and we're dealing with sequences in series, so it needs to be a whole number. So the nth term needs to be 32. So yes, calculation check as well. Here you can just built in here. Just want to delete that, equals space, and there's the calculations. The 31. Yes, so 1,000 to the power of 1/2 or square root of 1,000 is 31.6228, and here's rounded up 31.6. And so we need n is greater than that, so n is 32 terms to ensure accuracy to within 0.0005. And now let's look at a quick theorem. Here's a theorem 3. So if we add the partial sum Sn to each side of the inequalities in theorem 2, so recall theorem 2 over here. So if we add Sn to both of these, notice here, so number Rn is equal to S minus Sn. If you add Sn to it, what we end up having is this will be S, then plus Sn there, plus Sn there. So what we end up having is, so we'll end up having is Sn plus the integral from the Sn plus 1 of infinity f of x dx. Then this can be less than or equal to S as opposed to Rn. This can be less than or equal to, now we have an Sn plus, plus like this, integral from n to infinity of f of x dx, like that. And I'll just box this whole thing out. And then now just for clarity, I'm just going to write even further. So this is because Sn plus Rn, that's just the partial sum plus the remainder of the partial sum after, relative to the total sum. This just equals to S. So yes, that's just Sn plus Rn equals to S, like that. Just fascinating stuff. So yes, the inequalities in theorem 3 give a lower bound and an upper bound for S, the total or the exact sum. They provide a more accurate approximation to the sum of the series than the partial sum Sn does. Yes, so now we have a lower and upper bound like that instead of just saying Sn. So we know we add the remainders to them, or the possible values of the remainders, or the limits of them. So now let's look at example 6, and this continues further from example 5. So it states, use this new theorem, so theorem 3, with n equals 10 to estimate the sum of the following series. There's a summation from n equals 1 to infinity of 1 over n cubed. This is the exact same as the one we were dealing with in example 5. So this is 1 over n cubed. So exact same one. So we used the values from before and the formulas we derived from it as well. Yes, so the inequalities in theorem 3, yes, they become, so the inequalities, we're just going to plug this in, so we're using S10, we're using the nth term, the 10th term for n, so S10 equals 2, so we have S10 is S10 plus, now the integral from, this is going to be from 11, so this is n plus 1 to infinity of f of x dx, and now our fx will be 1 over x cubed, so it's going to be 11, and it's going to be infinity. It's going to be 1 over x cubed, 1 over x cubed dx, and this is going to be less than or equal to s, and this is going to be less than or equal to, and now we have S10 as well, plus now we have S10 infinity 1 over x cubed dx, like that. And now, from example 5, we already know that, the formula for this one here, let's go back to example 5, where we derived here. So the integral from n to infinity of fx dx, where fx equals to 1 over x cubed, it's going to be 1 over 2n squared. So we could replace that whole thing with 1 over 2n cubed, squared. So we get S10 plus, now we're going to have a 1 over 2, now the n is going to be 11 squared, like that. This is going to be less than or equal to s, and which is going to be less than or equal to S10 plus, and now what we have is a 1 over 2, and now the n is 10 squared, like that. So yes. And now using S10, or the 10th partial sum, as being 1.1975 and then 32. Note the extra 32 is just a more fine-tuned calculation in my calculus book, or my calculus book uses, which my OneNote automatic calculator cuts off. And again, remember, this is from example 5, where the calculus book had it here, but then they just added now for example 6 an extra 32. Just scroll up to it. This is example 5. Recall that this was for part A, 1.1975, which is the 10th partial sum. This is an approximation. Yeah, this is just a sum of all these terms, and this is S10 right here. And my calculus book cuts off here, and I mean my calculations cut off here, my OneNote, but also calculus book doesn't add the 32 there. But anyways, they added for the example 6. So going further, so using S10 as that, to put it in here plus this term, and then it's going to be in between over here, then plug it in here as well, S10 plus that this term right here, 1 over 2 times 10 squared, which is 1 over 200 as before. We get this right here. So we get the sum is between 1.201664 and 1.202532, and here's a calculation check, my OneNote, so we could just have just erase it just for completeness. So 1.197532 plus here plus 1 over 1 divided by 2 times 11 squared equals, automatic calculates exactly this number. And this way here, 1.97532 plus 1 over 2 times 10 to the power of 2, or squared. Erase this. Automatic calculation. Absolutely amazing how this has an automatic calculator built in while you write notes. So going further, so if we approximate S, you notice these are exactly the same thing then. So if we approximate S by the midpoint of this interval, so the summation approximated by the midpoint of this, these are the limits. So this is the lower bound, that's the upper bound. Let's just take the midpoint or the average. Then the error is at most half the length of the interval. So yes, the full interval is the full error possibility. But if we go exactly in the middle, so we're going to have error of at most half, because it could be lower bound and upper bound or set in motion right there. So the interval length is, if you subtract these, 1.202532, so that's upper bound minus lower bound, 1.201664. We get this value, and you can see it's exactly that equals that. So 0.00 zeros and 868, but we're going to take the midpoint so that we could split this in half. So the midpoint or average value is 1.201664 plus 1.202532. Divide this by 2. Or you could just divide this by 2 and add it to add this to this, or subtract from this. Then it's equals to 1.202098, and you could round up, my calculus book does, to 1.2021. Thus the max error is half the interval length. So we get, just divide this by 2. 0.000868 divided by 2. Yeah, and also I meant here to divide this by 2, and then you can add it to this or subtract from this. Anyways, so the max error length is 0.000868 divided by 2 equals to 0.000434. Let's completeness check it again. Equals, and there it is, automatic calculation there. And then it's less. And note that this is less than, there's 3 zeros and there's a 4. That's less than 0.0005. Which, recall in example 5, we needed 32 terms to ensure accuracy of 0.0005. So this one, notice here we're just having 10 terms. So that's fascinating stuff. So what we end up having is the series. So the series, like this, infinity n equals 1 of 1 over n cubed is approximately equal to 1.2021. So that's approximately that, and with error less than 0.0005. So yes, fascinating stuff. So yes, if we compare example 6 with example 5, we see that the improved estimate in theorem 3 can be much better than the estimate Sn is approximately equal to a partial sum of S is approximately equal to the partial sum Sn. So to make the error smaller than 0.0005, we had to use 32 terms if we were just using Sn in example 5, but only 10 terms in example 6 because we found the error bounds up and bottom and we took the middle. So that means we could just split that in half, the actual error length inside. We get this 0.0005 with just using 10 terms. So without having to actually calculate or needing 32 terms to get approximate S right there. So yes, fascinating stuff. So now let's look at the last part of this video, and that's the proof of the integral test. So we've already seen the basic idea behind the proof of the integral test in earlier figures for the series of 1 over n squared and 1 over n square root, right, or power of 1/2 like that. So if you scroll all the way up, you'll see what I mean. So those were specific cases, but now we're going to do a more general proof of them. Scroll all the way up, so we're going all the way up to here. So we started off looking at, this is the curve y equals 1 over x squared. So this is the series 1 over n squared like that. And then we were looking at to the left of it. Then we found that this actually converges. So yes, that converges. And then likewise for the other term right here, so for 1 over square root n, or 1 over n to the power of 1/2, I showed that if using to the right side, we could show that this is greater than the diverging one. So in other words, it's going to be divergent for that case. And this was a divergent over here. So yes, the series is divergent, and so on. So those were specific cases. So basically the integral test recap. So suppose f is a continuous positive decreasing function on 1 to infinity, and let an equals fn. Then the series of an from n equals 1 to infinity is convergent if and only if the improper integral right here is convergent. So from integral from 1 to infinity of fx dx. In other words, if this is convergent, then the series is convergent if the integral is. If the integral is divergent, then the series is divergent. So yes. So that's the integral test. You just check the integral, and if it's divergent, the series is divergent. If it's convergent, the series is convergent. Just fascinating stuff. Let's just scroll all the way down here. So yes, here's the proof of the integral test. So we've already seen the basic idea behind the proof of the integral test in the earlier figures for the series of 1 over n squared and 1 over n square root. For a general series an, look at the following figure. So figure 1, label it just easier for the proof. So I'm going to write this here. So rectangles below fx. So if we have rectangles below, so we're going to do like this. So we have x, this is y, and then what we have is a function like this. This is our y equals to f of x, like that. This is our 0. Let's say we have 1 like this. This is our 2. This is our 3. Let's go to all the way to 4 and 5 and so on. And it's going to keep going on, and we have all the way to n. Like that, and this is going to be dot, dot, dot. I'll move this in the center, like that. Alright, so let's say we have, we're going to draw to the below it, so I'm going to draw this in red, like that. So what that means we're going to be looking at, for this one, we're going to look at this rectangle across here, like that. This is going to be our A2, so when we have below, it's going to be A2, and this will be to the left of it, like that. Rectangles, yeah, so below the curve, this is A3. Likewise here, A4. Likewise, again, A5. And then it keeps going on and on, all the way until our AN here. So something like that, AN. Alright, so now what I've done is actually just added some more text here, just shifted around the proof just a bit more clear. So the area of the first rectangle in figure 1 is the value of f at the right endpoint of 1, 2, the interval 1 and 2. So the value of the value of the area, or the area is the value of the f at the right endpoint. Because remember, all these lengths are 1. So all these widths are 1. So then this height is going to be, right here, this height is going to be, that's just f of 2. from interval from 1 to 2. So this is going to be f of 2. So this area A2 is going to be just f of 2 times 1, which is f of 2. Again, as in the earlier figures at the beginning of this video. Yeah, so that is f of 2 is equal to A2. This equals to A2, like that. So comparing the areas of the rectangles with the area under y equals f of x from 1 to n, we see that, and here I'm just going to write that formula down here. So these areas are going to be A2 plus A3 plus dot dot dot, and then all the way to plus AN. So all the way to plus AN. Notice that these are going to be less than or equal to just the integral from 1 to n. So from 1 all the way to n. Notice here, so we're starting from A2 there, because we're shifting it, we're going to be below it, so we move to the interval to the right of it, the right-hand side there, and look to the left. So this, sum of these rectangles can be less than, and those are the series less than, and this can be f of x, the integral from 1 to n of fx dx, like that. I'm going to box this out. So this equation, or this inequality, is based on this figure. So let's go further. So notice that this inequality depends on the fact that f is decreasing. And again, that's based on the integral test. So we're assuming it's decreasing. As it goes to infinity, it's decreasing. So likewise, figure 2 shows that, and now here figure 2 is rectangles above f of x, like that. So instead of using x equals 2 there, or A2, we're going to use A1 and look to the right. So let's just draw this out. It's more general, like this. This is x, this is y, and now what we have is our 0, and there is our function. It's going to look like this, and so on. So now what we have is, let's say this is our y equals 2 f of x. So now what we have is let's say we have a value here. We'll call this 1, this is 2, we're going to have 3, we're going to have 4, we're going to have 5, and it's going to go all the way to, let's go to n right here. Except the interesting part here, because we're dealing with the left-hand side and moving to the right, so that's n there, we're going to be looking at an, and this starts off, so this starts off from A2 all the way to an, but this one we're going to be going towards from an minus 1. So let's just draw this in red now. So now I'm going to draw this above, the rectangle is above f of x, like that. So we're going to go across like that. So this is our A1 now, because we're using the left side here. And remember, the height of this is going to be, well, this is just going to be f of 1. And this is length is 1, or the width is 1. So that means the area is just going to be f of 1 equals f of 1, like that. Or just move it over like that. A1 equals to f of 1 times 1 just equals to f of 1. So yes. So going further, so now the second one here, this goes like that. This is our A2. Likewise here we get to A3 like that. And these are, remember, these are always above this function f of x. So now we have over here A4 like that. And then so on and so forth, goes across there, goes across there, and goes across there. And then now this one, remember, this is we're using the left side there and moving right. So this is going to be an minus 1. So this is going to be an minus 1. And now the inequality in this case, this one here we have the rectangles are less than the integral, but now it's the integral is going to be less than the inequalities. This one, remember, this one's from 1 to n. It's also going to be actually from 1 to n. So from 1 all the way to n there. So we're going to have the inequality from 1 to n of f of x. The integral from 1 to n of fx dx. And this is the area underneath the curve is going to be less than or equal to. And now we're going to have this a1 there. So a1 plus a2 and so on plus dot 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 all the way to plus an minus 1. Alright, so now that we have written all this down here, I just boxed it out as well. So thus we have two scenarios we can have. So if the integral from 1 to infinity of f of x dx is convergent, then we can look at figure 1 and see what it gives. So figure 1, because it's below it, it's convergent, we want it to show that's also convergent as well. So what we end up having is this is a2 plus a3 plus all the way to an. So So that inequality, or that series we start off with, is we get, I'll just write this down, so a2 plus a3 plus dot 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 plus an. This can be written as a sum or a series. So we have it as, this is going to be I'm going to write I all the way to n. I equals to 2 of ai. And then this is going to be less than or equal to, yeah, and this one here, this is all the way to n. So remember, this is from 1 to n there. So that's going to be less than or equal to integral from 1 to n of f of x dx. But then this one right here, so we know this is convergent. And this n, this is obviously less than infinity. So this is going to be less than or equal to, and it's from integral from 1 to infinity of this f of x dx, like that. And again, this is all since f(x) is greater than or equal to 0 there. So it's always positive. So yes, it's always positive, yes, so we don't need to worry about some sort of negative part right here where this becomes less than it or something like that. Yeah, so thus what we end up having is, so thus we have, I'll say the partial sum Sn. This is going to be equal to, because we were missing the a1, so we'll just add an a1. So a1 plus, now what we have is this summation of n I equals to 2 ai, and now this is going to be, well, less than this number. So it's going to be less than over here, yeah, plus that extra a1. So it's going to be less than a1 plus the integral from 1 to infinity of f(x) dx. Let's like that. And since this is convergent, so we're given that this integral from 1 to infinity of f(x) dx is convergent. So what I'll do is I'll write this, let this be the number m. Yes, rewrote that. So let this be the number m. So just pick a number because it's a number. It converges. So we're going to have a number plus a converging number there. So it's a max limit. Yeah, so thus what we have is thus the partial sum Sn is going to be less than or equal to m. So in other words, it's bounded. So yes, and since Sn is less than or equal to m for all n, the sequence Sn is bounded above, or yeah, the sequence there. Remember, sequence is just a term, series is just addition of the terms. So also note that Sn plus 1, if we take the term right after it, this equals to, well, this is going to be just Sn, the total sum. Yeah, I mean the total sum of the partial sum up to the nth term. And again, yeah, this is a sequence because this is partial sums. So we're not going to be adding the partial sums. We're going to be adding the terms, which at any given term n is a partial sum. So at Sn plus 1, so the partial sum, just one more, when we add one more term to the partial sum Sn, this just equals to, so Sn plus 1 equals to Sn plus adding just another term. So adding the an plus 1 term. Now this is going to be, well, greater than Sn. And the reason it's greater than Sn is because since we're given that the function f of x is always going to be, well, it's always greater than 0. So in other words, since an plus 1, this is equal to fn plus 1. So from the triangle, from the rectangles. So notice here, over here. So yes, remember, this right here, f2 is equal to a2. So in other words, fn plus 1 is going to be a2 plus 1. Oh, an plus 1. So fn plus 1 is going to be an plus 1 right here. So I'll just put this here. An equals to fn, f of n there, and likewise an plus 1 equals to fn plus 1, and that we're given this function is always going to be positive, so it's going to be, as it gets smaller and smaller, it's always positive, it's always decreasing. This is also going to be decreasing as well, but it's always going to be positive. So then when you add another positive number to partial sum, we get it bigger than the previous. So yeah, so we have, so since an plus 1 equals f of n plus 1, where this is greater than or equal to 0, so you're always adding a positive number to it. Yes, so thus the sequence Sn of the partial sums is an increasing bounded sequence, and so it is convergent by the monotonic sequence theorem mentioned earlier above from my infinite sequences video. So let's go back up here just to recap on that as well. And here it is from that section of the video. So monotonic sequence theorem, every bounded monotonic sequence is convergent, and essentially monotonic is either increasing or decreasing. And if it's bounded, so what we have here, so here's an example. So it's increasing, the sequences are increasing, but it's bounded. So because it's bounded by this m, this L limit of it is going to be in between. It's going to be less than or equal to this m. In other words, it's going to converge. So hence it's convergent there. So the sequence. So the partial sums is convergent. So that means, yeah. So let's go all the way down. Yeah. So that means that the terms themselves are convergent because the sum is approaching. Yeah. So a finite number. That means the terms are approaching a finite number or converging to 0. Yeah. This is the partial sum. This is actually the total sum. Yes. Never mind that. So so yeah, same thing. So basically, if the partial sums are bounded, approaching, are convergent, that means, yeah, the total sums, obviously. The partial is, the total is as well. So this is just the total sum as opposed to just the partial sum Sn. This is, yeah, so this means that this series An is convergent. So yes. So now, if you look at the flip side, if we have the second scenario, if the integral from 1 to infinity of f of x dx is divergent as opposed to convergent, then what we have is the integral from 1 to n of f of x dx is approaching infinity as n approaches infinity. And this is again because f of x is always positive. It's always greater than 0. So if it's always greater than 0, then this number just gets larger and larger. So in other words, yeah, and it's divergent in the positive infinity as this n goes to infinity. But figure 2 gives, so let's look at figure 2 now. Yeah, but figure 2 gives that the area underneath this curve is going to be less than, so from 1 to n, it's going to be less than the sum of these rectangles, or the terms of the series right there. So in other words, the series is greater than the diverging integral as it goes to infinity. So in other words, this obviously has to diverge. This all the way to n minus 1 over there. So an minus 1 starts from 1. So let's write this down. Yeah, but figure 2 gives an inequality. So integral from 1 to n of f of x dx is less than or equal to, and this is going to be the summation. I'll write this as summation from n minus 1 all the way to I. So I is 1 all the way to n minus 1 of ai. This again equals to just a1 plus a2 and so on, plus dot 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 all the way till a n minus 1. And then I'm going to write this as, this is just going to be the partial sum of n minus 1, so s of n minus 1. Yeah, so what this shows is that Sn minus 1, the partial sum of Sn minus 1 is approaching infinity. Because this is divergent as n goes to infinity, because we have, this is going to be right here, this is divergent. So this is approaching to infinity of this integral is going to infinity as n goes to infinity. So thus, yeah, so thus I just erased that sentence there, wrote this instead. So thus Sn minus 1, partial sum of the n minus 1 term goes to infinity or approaches infinity as n approaches infinity. This implies that Sn approaches infinity, because if the one before goes to infinity, obviously then the one after is going to be going infinity, and thus the series An diverges. So yes, if the integrals it's going to be divergent to infinity, likewise the area underneath or area above it. So it's just, so yes, you can look at it geometrically. It's pretty straightforward. Anyways, that is all for today. Hopefully you followed along this another epic long math video. I find it's a great way just to get a bunch of info all in one place and all quickly, and you can just download the information to your brain if you watch it faster time speed, playback speed. So anyways, that is all for today. Hopefully you enjoyed this long video, and like always, you can download this these exact notes in a link in the description below, as well as Excel file, as well as viewing these notes on Steemit, and yeah, I highly recommend there. Anyway, that's all for today. Thanks for watching, and stay tuned for another Math Easy solution.